Howdy folks. So in this section what I want to do is I want to compare and contrast the limits that we saw in section 2.3 with those that we saw in section 2.4. So if you're keeping track of the book numbers, we're looking at section 2.3 versus section 2.4. And I don't expect you to have these numbers memorized or anything, but I want you to see that we studied two different types of limits, one in each of these sections. And so to help compare and contrast these, let's look at these three functions that I've given you right here. We've got the function f of x, the function g of x, and the function h of x. And I have a typo to correct here, folks. There should be no limit there. I'll get that fixed for your notes. We're going to take the limit in just a moment, but there should be no limit there. And my hope is that you see that there's some commonalities to these functions and there's some differences. We see that all three of these functions have a factor at least of x minus 2 in the denominator, and we've got something going on in the numerators. So in this first problem, I want to go ahead and state the domain of each of these functions. This is just a review topic. So notice that for each of these three functions, none of them are defined for x equals 2, and all of them are defined for all other numbers. So the domain of f would be the set of x such that x can be any real number, except that x cannot equal 2. And that's the same for each of the other two. So we'd have the domain of g and the domain of h are the same. So now what I'd like to do is I'd like to take the limit as we approach this exclusion in the domain of each of these cases. And before we do that, this is where I want to help compare and contrast the problems that we saw in these two sections. I want to imagine, which I'm not allowed to do, I want to imagine that I went ahead and did direct substitution on each of these three limit problems. If I were to do direct substitution on f of x, okay, I'm going to draw an arrow here. It's very important to me that you draw an arrow. You don't actually say that this equals 0 over 0. If you write equals 0 over 0, that's going to be false. It's going to be incorrect. So I'm not saying that this equals 0 over 0 or anything to that effect. I'm just drawing an arrow for this limit, and I'm going to say that it has the indeterminate form 0 over 0. Okay? So that phrase that I just used was indeterminate form. Let me write that. And I'm not going to fully define this right now. We will learn this later on in this course, this idea of an indeterminate form. But for right now, just take me at my word that we call it that. But notice how we obtained it. We obtained it by pretending we could do direct substitution, which we're not allowed to do. Don't write this part down. I didn't say that this equals 0 over 0 because that's a meaningless statement. And instead I just said the structure of this looks like 0 over 0. Okay, so let's go ahead and compute this limit now. Let's give that a shot. So if we want to compute this limit, this is the limit as x approaches 2 of x minus 2 times x minus 3 all over x minus 2. And we've learned how to evaluate a limit such as this. This is the limit as x approaches 2, and we're just left with the expression x minus 3. That is, this function and this function agree with each other everywhere, except for potentially at the limiting value. And this new limit I can evaluate through direct substitution, and if I do so, we get 2 minus 3, which equals negative 1. For this next problem, what I'd like to do is I'd like to identify again the indeterminate form here, or the form here. And here I have to scroll up to see what g of x is. So let's go ahead and get started with it. We'd say this is the limit as x approaches 2 of x minus 3 all over x minus 2. And we'll talk about the trouble that we get into now. But what I'd like to do is say, okay, I'm not allowed to do direct substitution on this problem. We saw that because none of these three problems had the value 2 in their domain. None of these, and a better way to say that is none of these three functions were continuous at the limit value 2. But if I were to do direct substitution, which I'm not allowed to do, I would end up with the value negative 1 over 0. Or more generally, I'll say that looks like a over 0, and I'll just say that this has the form a over 0. I want to clarify that I'm not calling it the indeterminate form. I'm just calling it the form a over 0. Okay. Let's go ahead and we'll answer this question in just a second, but let's go ahead and work this next problem where we've got the limit as x is approaching 2 of h of x this would be the limit as x approaches 2 of x minus 2 all over x minus 2 quantity cubed. And we could immediately start working this problem if we wanted to. But what I'm asking you to do here is for just a second, pause and identify the form. And I would say that this has the form, the indeterminate form, 0 divided by 0. We see that I'm not allowed to do direct substitution. However, if I did do direct substitution, the numerator would result in a 0 and the denominator would result in a 0. Careful folks, don't write this down. I am not saying that this equals 0 divided by 0. That would be incorrect to write that. But instead what I'm doing is I'm simply pointing at this limit right here and saying that it has the indeterminate form 0 over 0. So does it make sense why two of these, the first and the last, were what we call indeterminate forms? You don't know this word indeterminate yet, but you see that it's a different form than if we did direct substitution on this second limit right here. That's what I'm trying to highlight. Okay, so now let's go ahead and keep working on this limit question here, this middle one. And we notice that if I look ahead, I can't evaluate this through direct substitution. This is actually a section 2.4 problem. So what we'd like to do is let's evaluate this as the limit as x approaches 2, and let's pick a direction of approach. Notice back with this original question, there was no direction of approach. Let's go ahead and assign the direction of approach from the right-hand side of x minus 3 all over x minus 2. And what we see is we can go ahead and jump straight to the answer to this question by saying as x approaches 2 from the right, the numerator is approaching a negative number, -1, we mentioned that before, and the denominator is approaching 0, we said that before, but specifically the denominator would be approaching a very small positive number. So I'm going to go ahead and give the answer here, but I'll justify it in just a second. I'm going to go ahead and give the answer as negative infinity, and the way I would justify this answer is we'd say that it's -1 all over a small positive number. Does everyone see this notation that I used? And you will notice that in some of my older works I don't use this notation, but now I'm starting to use it, where we say we've got a -1, we saw that from before, all over a small positive number, and we know that that's equal to negative infinity. That was from our 2.4 discussion. If you missed that, if you didn't do your pre-work for 2.4, you'll want to review that, or maybe you'll want to review it anyway because it's been a day or two. Likewise, if we were to take the limit as x approaches 2 from the left of x minus 3 all over x minus 2, if we were to describe this behavior, well, the numerator would still be approaching -1, fine, all divided by 0, and here we're approaching 2 from the left, so that's a number to the left of 2, like 1.9 or 1.95 or 1.998. Okay. Folks, notice that I was picking those numbers. I wasn't actually plugging them into the expression, but if we take a number just to the left of -2 and then subtract 2 from it, we get a small, there's 0, it's approaching a small number, but negative. And so we've got -1 divided by an arbitrarily small negative number, and so that would be an answer of plus infinity. By the way, all of this information here is enough to tell us that the limit as x approaches 2 of f of x, oops, excuse me, this was not f of x, this was the function g of x, let's write that down, of g of x does not exist. Let's take a look at this problem here. In this problem here, this third example, we again started out with the indeterminate form 0 over 0. If I were to do some cleaning up of this, we get the limit as x approaches 2 of 1 over x minus 2 quantity squared. Notice that this expression here and this expression here agree with one another, except for at the limit value itself. And notice that now, after doing some of this rewriting, we end up with just the form a over 0 again. Now again, I'm still not allowed to do direct substitution, but if I looked ahead and I replaced any x in the numerator with 2, my numerator would be 1. And if I looked ahead and replaced the denominator with 2, which I'm not allowed to do, I would end up with 2 minus 2, which is 0. 0 squared is 0. So this has this form. Similar now to the second question that we worked. In this case, it doesn't matter which direction of approach I get, I'm going to wind up with an answer of positive infinity. And one way we can help justify that is notice my numerator would always be 1, regardless of what values that x takes on. And then here, whether I take x from the left or from the right, say I take 2.1 minus 2 or 1.9 minus 2, regardless, I'm going to get a small number. It might be small positive, it might be small negative, but then I square it. So that will always be, because when we take a number that's non-zero and square it, we always get something positive. This will always be 1 over a small positive number. And that's how we tackle that question there. The big thing that I want us to take away from this, folks, is that in the case where we had an indeterminate form like 0 over 0, we may end up with a question like what we saw in section 2.1, or we may end up with a question like we saw in section 2.4, and it just more work needs to be done. But always when I get to the form of a over 0, notice that's different than 0 over 0, the form a over 0, always when I get to that form, I can give some sort of conclusive answer. I can compute the limit to be infinity or minus infinity, or state that the limit doesn't exist. And these two questions here were our 2.4 questions. Folks, I hope this gives you a little bit of clarification. I'm going to finish the problem here, but I'm going to leave you to try this on your own. What I'd like you to do is I'd like you to go to Desmos, and I'd like you to roughly sketch each of these three functions. I'll give you a hint. They all have something interesting happening at x equals 2 on them, and I'd like you to sketch each of these functions. Be careful here, folks, when you sketch the first function. Desmos won't show the hole, but if you hover your mouse over where x is 2, you should find that there's a hole there, and it should match with the information that we got from these three limits. So go ahead and sketch the graph of each of these three functions. Sketch them here, and then I'd like you to try questions D and E on your own. Please, folks, take a stab at D and E. You may not be 100% correct with your answer, but that's okay. As long as you give it an attempt, you'll get credit. But what I don't want you to do is leave it blank. If you do find yourself having questions on this first page, please come by and see me, and I'll be happy to help you. Thank you, folks. That's all I've got for you for this video, and I'll see you in the next one. Thanks.